Welcome AP Physics, Electricity, and Magnetism students. Today's review video is on induction. As you can see, I split the last unit in our curriculum to two videos. We're going to be talking about the concept of induction in this video and looking at some examples. And then in the second part, we're going to look at a specific device, an inductor, that uses the principle of induction in an electrical circuit, and we're going to see how the inductor affects the current in the circuit. So that's review video 2. But in this video, we're going to first define magnetic flux. You already have the concept down from Gauss's law with electric flux, but we're going to just review it. Because you need that concept to understand the main idea here, Faraday's law and Lenz's law, and so that's going to be. We're going to do a lot of examples of these two laws here, and then the third part of the video, we're going to learn that actually when voltage is induced, that actually is electric field being created. So changing magnetic field creates an electric field. We're going to see that in the last part of the video. Okay, so let's begin. All right, so here we have flux defined, B dot product area, so the dot product between those two vectors, and you could write that as a scalar product of the length of the magnetic field vector, length of the area vector, times the cosine of the angle between the two. So here I have a little diagram to show you, this concept. So we've got a certain width to this rectangle, a certain height, and so the area is just WH multiplied together. And a lot of people don't realize or don't think of area as having a direction, of it being a vector, but in physics we define area as having a direction. The area vector points straight out of the surface, 90 degrees to the surface, straight out, and the length is obviously the magnitude of the area. So then the magnetic field, the angle between those two is right there. So a lot of students will mistake theta and think it's the angle between the magnetic field and the surface. And so like when a magnetic field pokes straight out of a surface, they'll say cos 90 degrees, oh, no flux. No, actually the theta, when a magnetic field points straight out of the surface, is 0 degrees. Cos 0 is 1, so we got B times area. So that's a mathematical definition. But as I said during electric flux, when we were studying Gauss's law, it's best to understand the concept behind what flux is. It's as important as the formula. So it really helps with the understanding. So like I got a piece of paper here. The flux is how much field pokes into or out of that surface. So that we have flux because the field is going through the surface, but when the field goes along the surface, we don't have any flux because it's not poking through the surface. So that's what flux is as a concept. Now, sometimes the magnetic field is not a constant over the area. Very often it isn't. Like, for example, maybe we've got a lot of magnetic field here and then a very little small amount over here. So the way to find the flux, you cannot use B times area because the B is a function and there's multiple V's all throughout the surface. So what you have to do is you have to imagine a tiny surface here, dA, area dA, and then you could find the flux through that surface by B dot product A because the B doesn't vary by much because the area is so small. And then you add up all the fluxes and all the little dAs, so you're integrating over the surface. So it's this concept turned into an integral. So that's also something we're going to look at examples of. All right, now that we have an understanding of magnetic flux, the main idea. So this is what humans figured out, how to generate electricity. This is an enormously important idea for the human race, okay? And so, as you know, with electricity, you need a voltage from Ohm's law for electricity to flow in a circuit. Now, that voltage can come from chemical reactions, like in the case of a battery. But also, in the case of your household electricity, the way that it's generated is by changing the magnetic flux in a coil. So that's what this is saying, that the voltage, the EMF, the electromotive force, is equal to the negative derivative of the change in magnetic flux with respect to time. The more rapidly you change the flux, the more voltage you get. Okay? So how do you change the flux? You go back to here, you see you could either increase or decrease the magnetic field. That will increase or decrease the flux, creating a voltage. So make this more or less. You could change the area. How could you do that? Well, in the case of a wire, maybe you could bend it up and crinkle it up into a smaller, and that would change the area. So that would also generate voltage in the coil. Or we're going to see in another example that you can have a magnetic field flying into a coil flying into a magnetic field region, or you could slide a bar on some rails, so you could change the area that way. Or you could change the angle. If you spin this coil and this loop, then what happens is the theta changes, and maybe when you spin it like this, so you've got magnetic field, magnetic flux, you turn it like this, and suddenly you don't have any more flux because you've changed the angle. So any change in any of these quantities or these variables will create a voltage in a coil, generate electricity. Okay, so that's how you generate electricity at a power plant. All right, so another concept, as I said, already mentioned, you could create voltage by sliding or sending a coil into a magnetic field region. The area is L times X. How far the coil has gone into the magnetic field region is X. So the area is changing as you're pushing that coil into the magnetic field region. And then so when you take the derivative of that, the only thing that changes is how the X coordinate of how far the coil's going in. So that's what we take a derivative of. That becomes velocity. So another expression for the voltage for a coil moving into or out of a magnetic field region is BLV. Okay? Lenz's law is how we figure out the direction of the induced current. And, you know, this is just me trying to write it in as few words as possible. You can look it up online or in a book and you probably get a more thorough explanation. But basically, the I induced creates a B induced in the opposite direction of the change in the magnetic field. Okay? So what do I mean by the change in the magnetic field? So let's suppose I've got B going like this, and then I decrease it. So the change is actually this way because I'm making the magnetic field smaller. So the I induced will create a B induced that opposes the loss of this. In other words, it'll come out of the loop. And so B induced will be this way, and so that's how we figure out the direction of the current. We'll see that more in other examples. So there it is, flux, and the main idea of both videos right here, that voltage is created by changing the magnetic flux in a coil. Okay? Let's now look to some examples. So here I got a couple examples. This is that problem I mentioned already. I've got a couple rails here connected by a resistor, and I've got this metal bar that I'm sliding along the rails. So also critical is there's a magnetic field present going down into the paper. Maybe this is like the magnetic field of the Earth, as you remember from the magnetic field lab that we did back when we were in school. The magnetic field in New York State, most of it actually points into the ground. There's a component, a smaller component pointing to the north direction, but most of it goes into the ground. So maybe I got a couple rails along the ground with a resistor, and I'm just sliding a bar, and this is the Earth's magnetic field everywhere. As I slide this bar, what's happening is the B is not changing, but the area is. You might be saying, how am I changing the area? Well, the area here is between the bar and these wires right here. That's the area that the magnetic field is going through. When I slide this bar to maybe over here, now I've got more area, a bigger area through which the magnetic field goes. So I am changing the area, I'm changing the flux. How does that generate magnetic, what direction is the current induced? Well, first of all, since I'm gaining more magnetic field into the paper, the B induced has to come opposite of that, out of the paper. So then what I do is I use my right hand rule to figure out the direction of the current. Now that I know the B induced, which way does the I induced go? So I'm using this right hand rule, not this one, right? Not that one, but this one. I put my forefingers in the direction of the magnetic field induced, and then my thumb down here representing this wire is to the right. So the current goes in the counterclockwise direction. That generates a force on the bar because we have current passing upward through this bar. And so by this right-hand rule, current, magnetic field into the paper, force in the backwards direction, I see that the force on the bar is in the backwards direction. You actually don't need all of that to figure out the force on a moving bar or a moving coil. It is always in the backwards direction of the velocity. Why? Well, from energy conservation. If I slide this bar and I make current, it's going to make heat in the resistor. So suddenly heat is created here. Energy cannot be created or destroyed, the total energy. So if I'm creating energy here, I've got to be losing it somewhere else. I have to be losing the kinetic energy of the bar. How do you lose kinetic energy of the bar? You got to have a force in the backwards direction. So any moving coil, probably just best to just put, without thinking through all the induction stuff and the right-hand rules, just put the force backwards, okay? It really is true from energy conservation. All right, this shows some basic calculations that'll come up in such a problem. First of all, the voltage produced by this rail, BLV, as I derived over here. That makes a current from Ohm's law, V over R. Here's the V, the BLV. And then the resistance. The force, I could find the magnitude, ILB sine theta. That's the force on a wire, this wire, in a magnetic field. And the sine theta, that's from the last unit, by the way, the magnetism unit. The theta is 90 degrees between the current and the magnetic field. Current this way, magnetic field into the paper. So sine 90, I left that off. I plug in the I here, right there. LB. I didn't finish up, but I could write another line with, variables combined. I'm just, again, showing you the highlights, the main thoughts behind this. And the power in the resistor, I could either use a mechanics equation, force times velocity, or a circuits equation, IV, or I squared R, or V squared over R. So any power formula, mechanics or circuits, will get you the power in that resistor. So that's example 1. Example 2, a spinning loop. So now what I have is a loop dimensions L, H, okay, and a magnetic field coming this way. That loop is on an axle right here, the light line that's spinning, omega. Remember from mechanics, omega is radians per second, theta over time. Now, before I go into some mathematical analysis, I just want to show you how I figured out this current going this way. So right now we've got maximum magnetic field because the magnetic field and the area vector are 0 degrees to each other. Cos is therefore 1, so the flux is maximum right now. The moment I turn this even 1 degree, suddenly I have less magnetic flux because maybe I have like 1 degree here instead of 0, so this might be like 0.99 instead of 1. So we're losing this magnetic field as we turn away from this orientation. So B induced has to oppose that change. We're losing this, so B induced is out of the loop that way. And then I use this right-hand rule, not this one, magnetic field coming out of the loop, like this, representing my pencil, and my thumb here points into the paper. So the current here is going this way, up, over, and down. In other words, in the counterclockwise direction. So that's how I figured out the current. All right, how do you analyze this for the voltage? First thing I do is got to get flux and then voltage through Faraday's law. So the flux is BA cos theta. Okay, so the area is obviously length times height. That's right here, highlighted, color coordinated for you. The theta, well, remember, omega is the radians per second. And if I multiply by seconds, I'm going to get the radians or the theta. So I replace theta by omega t, a basic formula from the mechanics rotation topic. So now that I have the flux, why do I do that? Again, the main idea, Faraday's law. take the derivative. The more rapidly the flux changes, the more voltage I create. So I take the negative derivative of that. So this is just the flux expression from up here. Now, BLH are constants, so there they are. They just, they don't affect the derivative. The derivative of cosine is negative sine, so that's where the negative went away. No negative because we had negative sine derivative. But why the extra omega? Well, if you just had cosine of t, then the derivative of that is negative sine of t. Okay, but when you have a constant times t inside the cosine function, then you have the negative sine of the same variables inside omega t. But by the chain rule, then you have to multiply by the derivative of what's inside. And the derivative of omega t is just omega. So that's why we have that extra omega there. Okay? Now sine oscillates between positive 1 and negative 1. So the maximum it could be is, this voltage could be is 1 times this. Oops, I think I'm graphing the current. Yeah, so this would be the current. For some reason I decided to graph the current. Okay, so the voltage over the resistance. Okay, so there is the maximum current. The minimum current would be negative 1 times all of this over R, and the sine function. Now how did I know the period was 2 pi over omega? Well, this goes through one, sine goes through one cycle when we have 2 pi inside the sine function. So if I plug in for time 2 pi over omega, I've got 2 pi over omega times omega. The omegas go away and I'm just left with sine of 2 pi, one cycle. So that's how I knew the period was that. So there is example 2, a loop spinning, the voltage and current generated a sine function. I'm going to do some more examples. Okay, so here's another example. We've got a circular loop of radius lowercase a and a resistance capital R and a magnetic field given by B0 times the exponential decay. So when you plug in time 0, you get e to the 0 or 1. So the magnetic field at time 0 is B0. Then the exponential gradually drops to 0. So the field goes from B0 down to 0. It's decreasing. So determine the mth, the power, and the total heat dissipated in this circular loop. Alright, so first thing, it didn't ask for the direction of the current, but again, I want to practice Lenz's law, because that, if you have a Faraday law, then usually there's a Lenz's law also, the direction, figuring out the direction of the current. So here's the original magnetic field, and then we're losing it. So B induced has to oppose that change. If we're losing this, to oppose that, you add more to kind of try and keep it constant out of the paper. Then we use not this right-hand rule, but this one, right? So you put your forefingers in the direction of the magnetic field induced, and then your thumb will show the direction of the I induced in the wire down below. So the current goes counterclockwise. Alright, so let's go ahead and calculate the voltage. Remember, first we got to get the flux and then take the derivative to get voltage. Faraday's law, right? So BA cos theta, so the B is right here, this whole expression. The area is pi r squared, which is A, right, for the radius of the loop. And then that simplifies to this. I move the exponential to the right to put the time dependence here and all the constants first, so that'll make it a little easier to take the derivative. Alright, so there's the flux with respect to time. It's changing, so we're going to have a voltage and a current. How much? We take the derivative of that expression. Negative d dt of our flux expression here. So the derivative of the exponential is just the exponential. But that would be true if we just had e to the t. But since we have e to the function, we've got to use the chain rule. So we've got to, in addition to putting e to the minus bt here, multiply by the derivative of what's inside here, which is negative b. Right? The derivative of this is negative b. So that also multiplies times these constants, and the negatives cancel, and we're left with the voltage expression right there. Next, the power. So Power we could use from circuits, V squared over R, or we could use IV or I squared R, any form that's convenient. Since we already have the voltage, let's just square that and divide by the resistance. So here's the voltage squared divided by the resistance. Moving on. So notice all the constants squared over here, right? B squared, pi squared, a to the fourth, b squared, and then the r wasn't squared, right? And then the exponential gets squared too, and the way you do that is you make it instead of e to the minus bt, e to the minus 2bt. Okay, so there's the power. All right, so next thing, the total heat dissipated. Now remember from mechanics, the way you get the power is you could do work over time. The joules per second gives you the power in watts. The joules, the energy, the work is power times time. That's only true if the power, or valid if the power is a constant number. Then you can multiply by the time over which it applies. But if the power is a function, you've got to convert power times time into an integral. Power times dt, power times time, added from one time to another. So in our particular case, we take our power expression here, this whole big thing, multiply by dt, and integrate. Now if they want the total heat dissipated, we want it for all time, from 0 to infinity. So then this, all these are constants, so I just bring them down here. The e to the minus 2bt integrates to e to the minus 2bt divided by 1 over, or multiplied by 1 over negative 2b. So there's the integration for the limits, and then I plug in e to the negative infinity and e to the 0. E to the negative infinity is 0, and e to the 0 is 1, so we have a minus 1 multiplied, giving us a positive amount of work. Again, don't worry so much about the details. Well, maybe worry about how concentrate on how the integral works, but the big idea here, what you want to study, is that the work or total heat is the integral of p dt. Okay? I suppose maybe another thing that you want to emphasize is right here to understand where all the terms came from right here. Okay, so that's another thing back there. Faraday's law applied. All right, so that was our third example, exponential decay and integrating to get the total heat. Kind of common in this induction topic. Let's move on to our fourth example with induction. This is actually our final example. So we've got a wire down here with a current that obeys this function. At time 0, it's I0 times 1, and then notice we have 1 minus this, so the current is initially decreasing by this function. Then you've got a rectangular loop, dimensions b by c, and the questions are determine the flux, the magnetic flux in this loop, and the voltage. Okay, so this is a kind of classic flux calculation. When we studied this the first time in class earlier in the year, I said this comes up every 2-3 years. So it's a good thing to know how to do this, how to calculate the flux. What you have to realize is you cannot just use B times area, the algebraic expression, because the magnetic field varies throughout. Okay, so mu 0 I over 2 pi r. The further you are from the wire, the weaker the magnetic field gets. But if you move in this direction, the magnetic field is a constant. This way it's decreasing. So what you could do is you could find the flux in a very small area as long as you make the area lined up with the constant magnetic field. Same B all along this surface. So you could say B times area for this is the flux in that shape, that rectangle. And then what you're going to do is find the total flux by adding up the flux in each rectangle. Starting here, add, all the fluxes in all the rectangles. That's what we'd mean by integrating. Oops, I forgot the coordinate A is, this is A, how far away the hoop is from the wire, and this is B, the dimensions of the hoop. So we're starting here, radius A, and then we're ending at radius A plus B. So start here and there. This is A plus B. Those are the limits. So here's the magnetic field, mu 0 I over 2 pi r. Now, yes, it's this, but I'm going to try and just save a little time and write it for I right now, and later I'll put in I later so I don't have to keep writing all those variables. Now, the area dA is the area of this rectangle, this, which is C, times this, which is dr. So C dr is the area of that shape. So I have B times area, and I'm integrating that. B dA integrated. I highlighted the variables. Everything is a constant except for the dr and the r. So I'm integrating dr over r, which gives me the natural log. And I gathered the constants up front here. Then I plug in my limits, a plus b, and then a. And then I could combine the logs into one log. And I replaced what I was here, this whole expression. So there's the flux. Notice it is a function of time. It's changing. It's decreasing. And so there will be a voltage produced in this coil. The next thing we're calculating is the voltage. Okay? So that's over here. Before I jump into the details, it didn't ask for the direction of the current, but I want to review that yet again. So this current is decreasing initially. That means the magnetic field is decreasing, caused by this wire. So this B here is getting smaller. So B induced has to oppose that change, so we're going to have B coming out of the paper to oppose the loss of this. So once again, we don't use this right-hand rule, we use this one. We put our forefingers in the direction of the magnetic field induced. So this is B induced. This will be I induced. It's going to go this way, this way, this way, this way, again, counterclockwise. All right, here are the details of figuring out the voltage, which is part B. So we're going to do the negative derivative of the magnetic flux, this expression. So I plugged in the magnetic flux expression here. Everything is a constant. Here are all constants. These are all constants. The only time dependence is right here. So I'm taking the derivative of this expression with respect to time. The derivative of 1 is 0, and the derivative of alpha t squared is 2 alpha t. Okay? And then I just touched things up and combined things. The 2's went away, as did the minus signs, and there's the expression for the voltage as a function of time. Once again, I've indicated what I would like you to focus on. The thoughts here. This is just taking that whole big expression for flux, putting it in. And then the derivative, this is the only time dependence part. We take the derivative. So just understand this. Don't get too bogged down in the details, but just be confident that you can generate these details. Know where they came from, but don't go ahead and try and memorize them. Just make sure you can follow the thought process. Here is what the important part is here, that the flux is the integral of B dA from here to there. And also know that the dA goes this way, not that way. Okay? So this, and then also that this integrates to natural log. Okay, so this is what I want you to focus on. The thought process is here for when you study. Okay. Now, finally, we are in the last topic here for this video. So, voltage is basically the presence of an electric field. Remember, one of the definitions of voltage was the electric field integrated along a path, like a wire, for example. So this is Faraday's law right here, right? This is what I already wrote out. That voltage, the mth, is negative change of flux with respect to time. But what I'm just realizing is that the voltage is the electric field integrated along a path. And if this is a wire loop, then the path is closed. That's why that circle, right? It's a wire loop, like a rectangle we saw in previous problems. We saw circles, but it goes, the integral is around something and it starts and ends at the same point. And also, remember the math statement, the dot product says that the electric field has to actually be parallel or tangent to the path of integration. That's what the dot product with the vectors means. Like if I'm integrating along this line and the electric field goes this way, like my pencil, and this is my integration, then this is 0 because the dot product of the ds and the electric field, 90 degrees, dot product is 0. If the electric field runs along the integration, then the dot product is E ds, cosine is 0 degrees, that integral is non-zero. So a voltage is an electric field running along the loop, driving the charge, making a current. That's the concept here. This, by the way, is one way, the way we express one of Maxwell's equations in high school with high school calculus. You know, there are more sophisticated ways. But this is one of the of Maxwell's equations. I'll mention it in the next video. All right, let's take a look at one example here. So what I have is a solenoid of a radius capital R. And the magnetic field inside of a solenoid from the last review video is mu0 Ni. This is the turn concentration of the wires. How many wires per meter as you're wrapping that solenoid with wires. And the current is alpha T. In other words, it's increasing in the solenoid. So I want to determine the electric field for R less than R, in other words, within the solenoid, and R greater than R outside the solenoid. So yes, changing magnetic field creates an electric field as I see here. Now how did I figure out the direction of the electric field? So this magnetic field is, suppose it's the magnetic field of the solenoid. You'd figure that out with your right hand rule depending on which way the current was going in the solenoid. And then that's increasing. All right, it's because of this expression. Current's getting bigger, so the magnetic field gets bigger. So we've got to oppose this increasing by making B induced go into the paper. And then so we put our forefingers into the paper. We see, we used to say this was the current, but now it's the direction of the electric field going this way around. So yes, changing magnetic field creates an electric field. Okay. So we start with our expression of Faraday's law here with electric field. I put absolute values because I already figured out the direction of the electric field, so all I'm concerned about is the magnitude now. So this is like Ampere's law. When you calculate the electric field integrated over this path, it just ends up being E times the circumference of this circle, 2 pi r. So see, this is in pink. So I showed you that's the circumference of that loop there that I'm envisioning. And then the flux is B, this expression, Bn, and then alpha T for I. So Bni times pi r squared. Okay? Pi r squared is the area of this right here. So this is the flux, B times area right here of this surface. We do a time dependence, everything else is a constant, so we just take the derivative with respect to time. And so you see here we have the same variables with t to the 1, derivative of that is just 1. And so I rewrite this by dividing by 2 pi r, and I have constants here times r. So you see that the r, the electric field, is 0 in the middle, and then it gets bigger the further you get out. There's an r dependence inside the solenoid. Outside the solenoid, I use the same idea here. Electric field, that's the voltage around some loop out here, is equal to the derivative, the rate of change of the flux through this loop. Now, the left side just becomes like in Ampere's law. Instead of B ds integrated, it's E ds, which integrates to E times 2 pi r around here. Now the flux, it's B times area. But notice I don't have little r here like I had here. The reason I had little r here is because the magnetic field was all throughout this loop inside of our solenoid. But when I make the loop out here, the magnetic field is only inside the solenoid, not in this gap. So the net magnetic flux is confined to this pi capital R squared, right there. B times area, this area, not the whole area. So once again, we have a time dependence right here. By taking the derivative of that, it just becomes 1. So it's all these constants times 1. And I touch this up when I divide by 2 pi r. And I write the 1 over r separate so I could see that the E is greatest near the solenoid, and then the electric field gets weaker the further you get out. Last thing I did is I plotted the electric field, E, so it rises linearly inside the solenoid. And then outside the solenoid, it falls off as a 1 over r. Once again, I put these here in case I'm sloppy, and this might not look like a straight line. I put proportional to r to make sure the person grading it knows it's a straight line, that I want it to be a straight line, and this, that it's a curve descending proportional to 1 over r. The transition value right here, you could find by plugging in capital R into either of these functions, and you'll get these variables right here. So, that's the first video in the last unit of the last unit. What we learned or reviewed, what magnetic flux was, and then this big idea that voltage EMF is created by changing magnetic flux in a wire loop. Okay? We looked at a bunch of examples, the rail sliding, a coil spinning, magnetic field decreasing in a wire loop. Okay? And then current, once again, another example of magnetic field decreasing in a wire loop. Okay? So, all cases, we took the derivative of flux with respect to time. Okay? And then the last thing was that actually this voltage means that there's an electric field produced along our wire loop. Okay? I forgot to mention in this that I want you to emphasize, of course, these two steps here, the thinking behind those two. Alright, so that's the first review video in our last topic. I'll see you in the next video. Inductors.